Okay, ladies and gentlemen, welcome to this evening's Geology Lecture Series talk by Peter Ruggiero. First and foremost, if you didn't happen to put your signature on one of those handy-dandy little sheets, if you would be so kind as to do that on the way out. And here's the Hale Center shameless promotion that actually has nothing to do with me. If you have time tomorrow evening and are interested, there's going to be a fundraiser for the Egyptian Theater as well as Evolution Jazz Band on this same stage tomorrow evening. And so you might be able to find out more about that in a variety of places. I'm sorry, I believe the tickets are $10, and some of you probably know that. Also, Monday evening, there's the Coos Bay premiere of Ocean Frontiers, a film, also the same place, and that'll start at 6:30. So, also, the selfless plug is, if you don't have it scheduled yet, May 19th, the last talk in the series this year, Julianne Struve is coming here from Boulder, Colorado, and kind of a nice coastal connection to mesh with Peter's talk this evening, dealing with climate change and looking a little bit at the Arctic and what changes in the Arctic implications have for you. How many of you were at Dave Montgomery's talk? In the event that you weren't, after the talk this evening, I'll be out in the lobby. I've got a few extra copies of his book, King of Fish, that he signed before he departed, that we're selling as a lecture series fundraiser. And I also have a couple copies of Ore and Ore, the second edition of Geology of the Pacific Northwest, and a couple maps. So if you're interested, I'll be out at a table back there. This evening's speaker comes to us from Oregon State, and sort of reminiscent of somebody else that I know, started life back on the East Coast, went to Lehigh as an undergrad. I went north. Ended up at Oregon State for a master's and a PhD, and after graduating at OSU, he's kicked around the Pacific Northwest dealing with coastal issues, and actually told me at dinner that just a couple weeks ago was cruising through the slides of the southern Curry Coast down towards Sebastian Shores. So he's somebody that has done a lot of work along our coasts, and definitely will probably continue to do so for many years in the future. Also, it's the longest talk that I believe, title that we've ever had, and it deals with all kinds of stuff in the Pacific Northwest. Peter Ruggiero. And because it's just been a long week, we wouldn't be able to do this without the generous support of SWOCC, the SWOCC Foundation, the guys up in the booth that are live streaming and archiving this talk, and also Oregon Resource Corporation. Thank you.
Great. Thank you. Well, thanks very much, Ron, and thank you to SWOCC for having me down here. It's quite a pleasure to be down, and particularly on such a beautiful weekend, and I'm actually incredibly impressed that you guys all came inside this evening when it's so beautiful outside. Well, I'll be talking about some beaches this evening, so hopefully you'll vicariously think you're actually at the coast right now. Pictures like the one up here on the screen are ubiquitous scenes on coasts worldwide. When these kinds of situations happen, dune erosion with nothing backing the dune, it's not a problem for humans. What becomes a problem, obviously, is when we have coastal infrastructure, whether it's homes or businesses, et cetera, immediately backing the shoreline. And in coastal Oregon, we have quite a bit of coastal bluff and dune erosion. I'm sure all of you are familiar with scenes such as this one. In many cases, what we do in terms of protecting against the erosion, to protect our backshore infrastructure, is to build hard coastal engineering protection structures. Luckily in Oregon, a lot of this has been outlawed if you're not grandfathered in prior to 1977. But up in the community of Nesco in Oregon, the majority of the village is actually armored. And what's been happening in the recent years is several of the structures have actually started to unravel, causing significant problems for these backshore homes. And they're also dealing with flooding when the water gets up above the elevation of the crest of these coastal structures. So in the last decade and a half, particularly in the northern Oregon coast, there's been a perception of an increase in some of these coastal hazards, both flooding, erosion, problems with coastal protection. And so that's what I'll be talking about today. Much of my work over the last several years with myself and my students and colleagues has been really trying to understand problems like this picture that was taken in Ocean Shores, Washington during the last major El Nino event of 1998. Basically what we're interested in is how often does this kind of thing happen, and when it does happen, how significant is it in terms of coastal erosion, and what kind of problems does it provide for the backshore communities. So with my very long title, basically be looking at both the role of sea level rise as well as kind of this increased storminess that we've started to see in the records over the last several decades, and the relative role in terms of both coastal flood and coastal change hazards. All right, so basically what I'm going to be doing is taking a total water level modeling approach in terms of trying to predict how high the water gets on the beach. And it's going to be very simple modeling to combine the different impacts that go into how high the water gets. So this is a fairly straightforward definition sketch. I have one actual equation with numbers, with symbols in it later on. I guess I'll have to go two-handed here. This thing's not working as well. All right, there we go. Basically, the total water that's achieved on the beach, what we care about is how often it gets to either the base of a dune in terms of promoting dune erosion or bluff erosion, or how often it gets up and over that dune crest or the crest of a structure in terms of coastal flooding hazards. And so that's going to be a combination. The total water level is a combination of basically the mean sea level, astronomical tide, which is a deterministic, easily predicted process, the non-tidal residuals, which is a whole bunch of kind of oceanography in terms of things like storm surge, wind blowing water across the continental shelf, pressure changes, and a variety of other oceanographic signals like El Niños, water temperature variations, and then finally the wave-induced signal in terms of how high the water gets, which is referred to as wave run-up. That's setup plus swash. Setup is a mean superelevation of the water level due to breaking waves. Waves actually, when they're breaking on the shoreline, they provide a force into the near shore and actually elevate the water level. And then swash is just simply the water going back and forth at your feet, causing you problems during your picnics at the coasts. Okay, so it's really the things we can measure from a tide gauge, which includes the astronomical tide, mean sea level, and the non-tidal residuals, plus the wave-induced components that combine for the total water level. And ultimately, I'll be combining all those to predict how high water gets and how often it gets there. In terms of climate controls on the total water level at the coastline, there's a variety of fairly straightforward processes that are dominant. Certainly, the global rise in sea level that we've all heard so much about, and really I'll focus in on the fact that we have to inform what we know globally with the regional variability, which is incredibly important. And so variability, the range between El Niños and La Niñas, has a very significant impact on the water levels, particularly during the El Niños. That slide I showed earlier, in 1998, water levels get elevated 30 to 40 centimeters higher than typical, and that lasts for months. That's on the order of several decades to a century worth of sea level rise that impacts our coastline for several months during the wintertime during major El Niños. The last two major ones we had were 82, 83, then 97, 98, and then the next one's going to cause significant problems for us as well. And then finally, decadal trends in wave heights because of that wave-induced component in terms of how high water gets. If the waves are changing, that's going to change the water levels as well. And I'll show you some evidence of increased storminess in a little bit. All right, so just to step back a little bit, this is a geology series lecture. We have to have some geology in here. As we all know, we're in the Cascadia subduction zone. We have the oceanic plates being subducted against the North American plate. Every 300 or so years, we have a major subduction zone earthquake. During the interseismic period, we actually have significant changes in the coastal elevations due to the geology offshore, and that informs the local variations in water levels along the coast. And in fact, there's quite a bit of variability in the Pacific Northwest. So up in the tip of the state of Washington, up in Nia Bay, we actually have sea level over the last several decades. So these plots go back, in some cases, back to the 40s and 30s. We have sea level is actually dropping over that time period. And that's the relative sea level, and that's because the coastline is actually being uplifted due to tectonic processes. In the central Oregon coast, say the Yaquina Bay, Oregon tide gauge, that's been in the water for about 40 years, we see a slight increase in water levels on the order of a little over about a millimeter per year, which is less than what the global rise in sea level has been over that time period, which is about 2 to 3 millimeters per year over the last several decades. The reason why it's less is, again, because of this tectonic uplift, but significantly less so than what we have in the northern part of the coast. And then down in California, we actually have a relative sea level rise that's even higher, and that's because of coastal subsidence in that location. So significant variability in what the land sees in terms of the water level from tide gauges. And we can take what we know about this tectonic uplift, and this is work done by Ray Weldon and colleagues at the University of Oregon, They've had very meticulous measurements of coastal benchmarks along the coastline, and they have estimates of what that vertical uplift has been from the tectonic processes, with some assumptions about what the sea level is doing in general in the Pacific Northwest. We can change that information from the tectonic variability to a relative sea level rise plot. And so what we've done here is basically taken raised data and turned it into on the order of several hundred actual kind of vicarious tide gauges along the coast to give us a lot of very detailed information about how this relative water level is changing throughout the coastline. And again, over the central northern Oregon coast, we have about 1 millimeter per year of rise over the last several decades. But actually, just south of Cape Arago in this area is when we switch over, and actually the coastline is emergent relative to the water level because the tectonic uplift signal, at least over these last 40 years, is higher than what the sea level is doing. And there's some weirdness up in Astoria as well. So significant variations in the vertical uplift rates basically have significant impact on what the beaches are seeing in terms of relative sea level rise. Okay, so in terms of basically past, present, and potential future rates of sea level, here's a plot that's a little bit different way of looking at sea level. Instead of just looking at the actual magnitude of sea level through time and projected into the future, what's plotted on the vertical axis here is actually the rate of sea level. So it's plotted here in millimeters per year. So it's basically the rate with which water is going up through time. And this is kind of a simplification of a lot of geologic evidence, but for the recent geologic period, the last couple thousand years, more or less, sea level has been going up a little bit less than 1 millimeter per year at a relatively constant rate through that time. The instrumental record comes in more or less the late 1800s. Some European stations predate that, but we start to actually measure what the global sea level rise signal is. Again, kind of the early part of the late 1800s, early 1900s. Got a lot of variability. There's a lot of discussion about when we see accelerations or when we don't see accelerations, but there is an acceleration in more or less the latter part of the 1800s, and so the instrumental record has picked that up. More recently, satellite data has shown that the last several decades the sea level rise is more about 3 to 3.5 millimeters per year, whereas the 20th century average is more like 2 millimeters per year. So there's potential for a second acceleration that we're seeing right now, but again, the scientific community's there's no consensus yet. And then what we show here is a range of predictions of what sea level will do in the future going forward. And you can see that even for the very low estimates of projected future sea level, and it's plots basically going out to about 2100, you see that we get into this basically parameter space of sea level rise rates that we haven't experienced for thousands of years. So the beaches are going to be seeing something, even at the low end of our predictions, that's very different than what they've experienced in recent times. Now, what I'm presenting here at the bottom of the panel is a range of sea level rise estimates to try to give you an appreciation for the uncertainty associated with our knowledge of the system right now. Only in 2007, the IPCC released their latest report, and they came up with a range of about 0.2 to 0.6 meters by 2100 in terms of where the sea level would be going. They did acknowledge that they weren't modeling ice sheet processes and the melting of ice sheets there, but almost immediately following that 2007 report being released, several different efforts came out that showed projections of sea level rise significantly higher than this 0.2 to 0.6. And these were ranges well up to the ones by 2100, so much higher. And even the most recent estimates, the National Climate Assessment is in draft form right now. This is a report that's coming out in 2013, but it's basically a national look at a whole bunch of different climatic variables. The sea level rise scenarios that they're looking at in terms of this report range from 0.2 to 2. So there's a huge range now in terms of where we think sea level might go in the future. We have a couple of reports coming out as well in the next couple of years. And very interesting, the more people and the more time we've spent studying this problem, unlike many other scientific problems, our uncertainty is actually increasing. So the more we think about it, the less we actually know, which is a little bit disturbing. This gives you a little bit of kind of an appreciation for the kind of the range of the estimates. Here's the IPCC estimates in 2007, and then immediately following that, Rahmstorf was one of the first. We see these ranges well up into the ones by 2100. And this, I mentioned the National Climate Assessment Report. These are the scenarios that they're going to be using, and in fact, these are the curves. So again, anything ranging from a low-end estimate of 0.2 to a high end of 2 meters. So again, a huge amount of variability in terms of where the sea level might go. And remember, these are now global projections that I'm talking about here, and all that information needs to be then corrected for the local situation based upon our tectonic situation here in Oregon. All right. Just one reason why it's so complicated and so difficult to actually get a decent number is just the variability of the system. Even over the time period, we've had incredible detailed measurements from satellites. Here's the satellite record from basically late 1992 to just about a year ago. And you can see for the Pacific here, a huge range in terms of what the sea level trends have done in that time. Along our coast, in those just last couple of decades, we actually see very little change. The plots I was showing before were from tide gauges that go back 40 to 50 years, and that's where we get this millimeter or so rise in terms of relative sea level. On the Western Pacific, we actually see rates of rise on the order of 10 millimeters per year, 4 or 5 times higher than the global average. So the satellites are picking up this incredible variability. This is forced by a variety of ocean and atmospheric dynamics, so it's quite a complex situation. And you can imagine just trying to predict what the water level will be doing at that spot right there is quite difficult. All right, so sea level, obviously a major climatic impact in terms of coastal hazards, coastal flooding, and coastal change. Another one that I mentioned is the frequency and magnitude of El Niños. And maybe many of you guys are familiar with this, but during, again, the El Niños, most of our coastline in the Pacific Northwest starts looking like this. A lot of coastal engineering structures go in, in the state of Washington is where the structure was. California has problems. And again, the reason for that is the water levels are elevated in the order of several tens of centimeters, and that lasts for months. We also have larger than typical wave heights in the Pacific Northwest during that time period, and they approach from a different direction than usual, which has significant implications for coastal sediment transport. And we get hotspot erosion in our littoral cells in Oregon. So El Niños are a big problem, particularly the major El Niños. And one big question that's out there is basically what's going to be the future frequency and magnitude of El Niños? And one question is, are there going to be more, less, no change from present day? People think about this in terms of kind of the low frequency oscillation of the climate system, in terms of a Pacific decadal oscillation. Myself and some colleagues have looked at the wave climate through the years and shown that during some of the big El Niños and La Niñas, we have, again, larger wave energy during those time periods. But really, if you ask the room full of climatologists whether we're going to have more El Niños or less El Niños, more intense El Niños, less intense El Niños, you'd get that many answers. Again, a significant amount of uncertainty in terms of where we're going in the future with the El Niño problem. All right, so talk about sea level rise and El Niños. Another thing I'll be focusing on is the wave climate of the Pacific Northwest. We're blessed or cursed, depending on your perspective, one of the most significant wave climates in the world. And we have extreme waves on the order of 14, 15 meters that have been measured by some of our buoys. But if you step back a little bit, here's a paper by a colleague that maybe some of you have heard of, Paul Komar, who's an emeritus professor at Oregon State University. He happened to mention work of some doctoral student named Ruggiero from 1996, who had predicted that the 100-year return wave height, so this was published in 1996, was on the order of about 10 meters for the coast of Oregon and Washington. And that work was done based upon a relatively short record of wave heights. The buoys hadn't been in the water very long. The records were spotty in some ways. And so that was the prediction as of 1996. However, based upon the 97-98 El Nino and the 98-99 La Nina, we had very significant coastal erosion problems in the Northwest. Paul and his postdoc at the time, Jonathan Allen, who works for the State Department of Geology in Newport now, they looked at the wave climate throughout the west coast of the United States. The record had now been about 5 to 10 years longer than when this guy Ruggiero had looked at it. And what they found is not only were the wave heights significantly bigger than 10 meters, in fact, there had been about 5 or 6 events in 97 through 99 that were actually larger than the 100-year predicted wave height. So obviously that number needed to be reevaluated. So while they were doing that, they actually found that a good number of the buoys along the west coast of the United States were actually showing a trend of wave height increases through time. And so they were looking at both the annual increase of the waves, just taking a one-year average, and also looking at just the winter waves. Winter's when we have problems in terms of flooding and erosion, so let's just focus on the winter waves. And the winter waves turned out were going up a little bit faster than the annual average itself. So luckily, that Ruggiero guy got his act together, and along with Paul Komar and Jonathan Allen, a couple of years ago, we looked at the data set now that was much more robust. But by now, it's about 35 years. We actually have some of the longest and most continuous wave buoys in the world with very high-quality records. And so we analyzed that data set, basically redoing the analysis that Komar and Allen had done in 2000. And we found very similar results. We found that if you just plot the annual mean wave height for a particular buoy, we saw a slow but steady increase, a statistically significant increase in that in the wave heights, and they were going up about 1.5 centimeters per year, enough to be able to be resolved by the buoys. If we looked at just the winter months, again, that's when we have our biggest problems, the wave heights were actually increasing a little bit faster, about 2.5 centimeters per year. And then if we just picked out the biggest storms, the biggest 5 events per year, the rate of those, there's a little bit more scatter in the data, but again, statistically significant rate of increase, about 7 centimeters per year. And then finally, just the biggest event per year, the biggest measured wave height per year, was going up about 10 centimeters per year. And these are still relatively small numbers. When you think about the fact that this record's now averaged over 30 plus years, 10 centimeters per year gets us a 3-meter increase in that biggest wave height. So now you have an idea of why Ruggiero was predicting the 10-meter 100-year wave height back in the mid-90s and why it's a much much larger number now. Another way of kind of looking at this kind of increase in wave height, kind of a proxy for increase in storminess, is looking at basically kind of a number distribution of the data. So here's wave height in meters along the x-axis, and basically the number of events that the buoy has recorded, wave heights of that magnitude through time. And I basically picked a decade at the very early part of the record, the 70s through the 80s, and then a decade at the latter part of the record, had the same number of measurements in each part. And you basically see a shift as you go from black to red, from the older part of the record to the newer part of the record. You get much higher number of these bigger wave heights. And you really see this increase out in the most extreme wave heights. So this kind of, again, is more or less what I showed in the last plot, but it just shows it a little bit more of a impressive way. So remember back when I talked about all the contributions into the total water levels, the wave-induced component is significant because it raises the mean water level due to wave breaking and then the swash oscillating back and forth in the beach. So if the wave heights continue to increase, they have the potential to increase coastal hazards. However, some folks have attributed these wave height increases to climate change, but this is a very difficult connection to make, and it's still an area of very active research. I'll kind of flip through that slide real quickly and just kind of move on to another recent study by Young et al. This came out this summer. This is now, again, looking at satellite data, so similar to the sea level plots that I showed earlier. This is now looking at the wave climate from from satellite altimetry. And the record here is only a couple of decades, so it's a little bit less long than the record from the wave buoys, but again, it's very robust because it's global. And basically what they looked at is both the mean wind speed and the mean significant wave height globally, and the areas of kind of warmer colors, yellows and reds, are areas where there was an increase during the last couple of decades. And you can see that the mean wind speed, for the most part, had a slight increase. Not much of a picture in terms of the mean wave height, except maybe something going off of the west coast of the United States. Again, these are very different kinds of measurements from satellites rather than the buoys. They also looked at the extreme events. So this is the 99th percentile wind speed. So it's just a wind speed that's only exceeded 1% of the time. And you can see much more of these yellows and reds. And so the plot here is basically a percent change in that value through time over a couple of decades. But you can see a significant change in terms of the winds getting stronger and the extreme winds getting stronger faster than the mean winds. And that is, as expected, it's winds over the ocean that are forcing the ocean waves. And you see a kind of a response in some ways to that wind changes. The significant wave height, particularly this extreme significant wave height, is going up a lot faster than the than that mean value. So this, again, corroborates what we see in the buoy data and shows the situation for a good chunk of the West Coast. Okay. Just one more way of looking at this. We were asking the question, why? The obvious answer is because of the winds. It's not a very simple thing to put together, but if the winds are getting bigger, the waves are getting bigger. The other thing to think about is just simply if you shift the mean of a distribution, the extreme parts of that distribution are going to get bigger faster. And so what I'm showing here is basically this is again, an exceedance percentile plot. This is the median wave height, kind of similar to what I showed earlier with the mean wave height going up about 1.5 centimeters per year. The winter means are going up about 2.5 centimeters per year, and those extreme waves are going up about 6 or 7 centimeters per year. And it's a very impressive continuous ramp in terms of the more extreme waves going up at a faster rate than the more mild waves. And it turns out this straight statistics will actually reproduce that same behavior. So I gave you kind of more of the physical response answer in terms of the winds are changing, that's changing the waves. But from a statistics geek like myself perspective, it's just if you simply change the median of a distribution that's described by a log normal distribution, then automatically the extremes have to go up faster than the means. And so that behaves quite well. But that's not a great thing for our coastlines because it's the extreme waves that are causing the biggest problems in terms of erosion and flooding. Okay, so wave heights and water levels aren't the only thing that people have been studying recently in terms of seeing a significant change on the extreme ends of distributions. Lots of folks have been working on this in terms of river flows, precipitation, heat waves, et cetera. And there's a very active area of science now in terms of trying to understand what's going on with extremes. Because in terms of societal vulnerability, people being impacted by kind of natural events, it's really the extremes. And people have started to say that kind of the assumptions that we've had in the past in terms of stationarity, that no longer exists. So stationarity is dead is a quote by Milley et al. From Science. And we get a situation where, again, getting back to the 100-year return level wave height, and that's kind of analogous to the 100-year flood. It's an event that has a 1% chance of occurring any given year. Well, that value today, which has a 1% chance of occurring, if we only go 25 years or so into the future, that might have a 30 to 60% chance of occurring. And so that's just what's plotted here with the data. These are estimates, again, of what this 100-year, 50-year return level wave height are. And you see that now they're no longer just single numbers, like that 10-meter value that we had in 1996. They're now time-dependent. Stationarity is dead, according to Milley. And just to step aside, again, the IPCC and many other folks are looking at this problem in terms of extremes. In fact, just about a few weeks ago, a report by IPCC came out as a special report simply on managing the risks associated with extreme events and disasters to advance climate change adaptation. So a lot of folks are taking this seriously. Again, heat waves, river flooding, precipitation, and in my case, wave heights. All right, so let's get back to the question that I initially posed with the title of the talk, and it was something along the line of what's the relative role of increasing wave heights versus sea level rise in terms of changing coastal flood and coastal change hazards. And we get back to this word equation. We talked about all the components that go into how high the water gets on the beach. And now that we know that the wave heights measured by buoys or satellites out here are increasing, that's increasing the delivery of energy into the near shore. So the waves that are breaking and generating elevations rising due to wave setup and run-up, that's getting bigger. And so now we need to be able to account for that. And so here's just to wake you guys up, my one equation with symbols. Again, not just the total water level at any given time is what we care about. We actually care about what the rate of change of the total water level is. So now going forward, so similar to the sea level rise things that we've been talking about, we want to know the rate of change of the overall total water level. So that is a combination of relative sea level rise. It's a combination of the rate of change of the astronomical deterministic component of the water level. If there's a change in the kind of this non-tidal residual, so that oceanography, the storm surge, et cetera, El Nino issues, and that would be impacted. And then this is the rate of change of wave run-up, so the wave-driven components. I'll ignore for now, and I can explain in detail later why it's not a bad assumption, these two pieces. And basically what we get is the rate of change of the total water level is basically a competition between the things that are causing the relative sea level rise to go up versus the wave-driven component. So we can actually compare the relative role of those two processes. And I won't show the equations that we're going to use to model the wave run-up, but I will just make a plug for the fact that a lot of the data that is used to generate those equations has been collected at OSU over the years. Rob Holman is a professor in oceanography there. He's developed image processing techniques using video cameras to measure the the leading surface of the water level on the beach, and really that's what the equations are using. And so we've had a lot of work over the years done at OSU to improve the science. And so the run-up elevation, how high the water gets on the beach, is a function of both the beach morphology, so things like beach slope, kind of the nearshore slope, the grain size, as well as the offshore wave conditions. So if the wave height, and I haven't mentioned the period very much, but if the wave period is changing, then the wave run-up is going to change and the water level is going to go up. All right, so in terms of putting that together, here's a plot that I showed you before, but in a different format. This is the Yaquina Bay, Oregon tide gauge record going back to about the 60s. And it basically shows about 1 millimeter per year in terms of relative sea level rise at that location. I showed the kind of mean wave height increase through time from the buoys. It's a little shorter record, but about 35 years or so. And the wave heights are going up about a centimeter and a half in terms of the annual averages. Of course, the extremes are going up bigger. But if we take the information about the wave heights, we use that to predict what the wave run-up is on the coastline. Using the models I just referred to, we can actually predict that the wave run-up is increasing at a rate of about 3.5 millimeters per year. And so that's about 3 times as fast as what the sea level rise processes are causing water level to go up. So if we put that together, we go back to our plot, we kind of combine the data of Ray Weldon and some of the tide gauge data. This is our alongshore variability and relative sea level rise along the Oregon coast, where we have coastlines that are actually the land is going up faster than the water, and some areas where the water only goes up slightly faster than the land. If we add now this information about what the waves are doing to the water levels that are achieved on beaches, now we see that the wave heights are actually raising the water levels on the order of about 3.5 millimeters per year, and that's much higher than what the relative sea level rise signal was. I showed you data from one buoy in kind of the northern part of Oregon, southwest part of Washington. We got another buoy kind of off the southern part of Oregon that shows slightly less changes, but they're still there. And so there's the rate down there. But if we combine them with some semi-intelligent straight line in between, we see that regardless of where we are along the Oregon coast, if we believe the data in the models, the wave height processes are causing the total water level to go up faster than just relative sea level rise by itself. And in fact, so it's really adding these two together in terms of what the total water level is doing. And areas that might have been emergent in terms of the land, the tectonic processes causing land to go up faster than what sea level is doing based upon what a tide gauge would tell you, the wave-induced processes are actually causing water levels to go up faster than those tectonic-induced land changes. So we are potentially experiencing problems down here as well. All right, so in terms of taking this kind of information and going forward, I'm just going to show a couple of kind of fun plots where we can actually compare and contrast these different processes. Everything I showed you earlier is basically what's happened in the past using these data sets and simple models. And now let's kind of move forward in time with a variety of different scenarios about what sea level might do and what the wave climate might do. And again, the approach I'm taking is trying to understand how often waves are going to be banging into a dune like this or overtopping the dune. And I'm going to define a parameter that we'll look at. And basically, it's the impact hours per year. Both the tide gauges and the wave gauges are measuring data every hour. So we can actually make these calculations on an hourly basis with some knowledge about what the beach looks like. We can actually predict where the water level is on the beach every hour. And so we can average that over maybe a 10-year period of data and come up with a parameter called impact hours per year. It's more or less a proxy for how often we'd have either erosion or flooding for an elevation that gets us up over the crest of the dune. So that's what I'm being here by these BF elevations. These are backing feature elevations. So 4 meters is probably the base of this sand dune. So the red line is basically how often we're getting to that elevation, whereas the 6-meter elevation is the crest of the sand dune. That's how often we're getting above the crest of the dune and causing flooding. And so what I'm doing here is just basically for a whole range of potential sea level rise projections into the future, we're looking at the rate of change of the impact hours due to sea level only. And so we can make a variety of plots for various changes. We have 20 centimeters of sea level rise in a couple of decades. We can see that the number of hours per year with which we get to a certain elevation is going to change by somewhere between 20% to up to 100%. For some of these higher rates of sea level rise projections, the values go up much higher. So we can actually quantify with these simple approaches for various projections into the future how often waves will be banging into dunes or causing problems. And we can do the same thing with the wave height processes, because these simple models can isolate the waves from the water levels. And without getting into any of the details of what's going on between these messy curves here, the bottom line is any value over this black line of 1 means that the wave-induced processes are again causing the total water level to go up faster than the sea level rise-induced processes. And so the waves are more important. And there's a variety of different scenarios we ran here, but it's basically the ratio of the rate of change of impact hours due to waves versus the rate of change due to basically sea level rise. Anything above 1 means that the wave heights are more important. So basically now we've shown for more or less the last 30 years, plus a variety of potential scenarios out into the future, that the wave height increases may remain as least important or more important than kind of global rise in sea level for the next couple of decades. Now, certainly, I'm not trying to argue that we should forget about sea level and not study it anymore and just worry about waves, but the point is that we should be accounting for both processes, and for the most part, people have not been dealing with that in terms of thinking about coastal management up until this point. So getting back to one of the pictures I showed earlier, this is back to Nesco in Oregon, where it is a significant problem when the water gets just above the elevation of this crest. So the ground elevation is about 25 feet. As long as you're an inch above 25 feet, it's causing problems for their living rooms right here. Over the last 30 years, based upon our measurements, we can compute that the total water level has increased by a little bit less than a foot at this region, combining all the processes, and 70% of that is due to the waves, and the 30% is due to the global rise in sea level. And so it's really the combination of these climate-controlled processes that need to be included in both engineering design. So we design coastal structures for things like the 100-year return water level. In terms of coastal management, that's how we design setback in terms of where coastal development can occur. So both of those need to be accounted for, and we need to account for the significant uncertainty. I alluded to how uncertain our projections are of sea level. Our projections in terms of what the wave climate might do are even more pitiful than that. Okay, so I'm going to now move to a little bit different thrust in terms of this talk. I've kind of talked about the data and kind of the relative role of waves versus sea level. And now I'm going to kind of talk about some of the more applied work we're doing in terms of trying to get this information to coastal decision makers and planners in a way that hopefully they can start using it to help with decision making. And so really what we're after is trying to develop ways to incorporate the uncertainty associated with these climate change and variability. Keep in mind that I'm not attributing the change in wave heights necessarily to human-induced warming, okay? But we want to get that information into coastal vulnerability assessments. We're looking at flooding and coastal change hazards. We're thinking about present conditions, so what might happen with a storm that occurs tomorrow, maybe an emergency management application, as well as future conditions, coastal planning, okay? And we want to do this in an integrated, multi-hazard, multi-scale way, and probabilistic is a key word as well. I will step back and say, I'm not sure how many folks know this, but Oregon is actually one of the few states that actually historically has had some actually science-based coastal hazard maps that have been produced by the State Department of Geology. Their work in terms of mapping tsunami hazard zones is very well known, but they've actually done this similar work for coastal flood and coastal change hazards. And these have been around since about 2000. Jonathan Allen at Tagami developed these. And it's a series of lines on maps. And I don't think the entire coast is mapped, but a good number of the communities where people live have been mapped. They're deterministic event selection approaches, meaning they just pick a couple of different scenarios, so some big combinations of waves and water levels, and using some simple models, project where the water might get or where the erosion might get to for that particular event, and overlay it on aerial photographs, and you can see how that might impact some folks. These are very simple models and simple products. They're relatively conservative, but they have been used by a variety of stakeholders for a variety of applications. So it's great that we have those. But now, in the last decade and a half, we've got a lot more information, a lot more understanding about what climate change might do, what the climate impacts are, what the variability in terms of the wave climate looks like as well. We want to be able to incorporate morphological variability into this kind of approach as well. There's a significant societal need to also update the approach in terms of population development pressures increasing. Coastal planners and citizens are actually asking for this kind of increased sophistication of information. I mentioned, communities like Neskowin have actually this perception that the problems that they've experienced have been getting worse, not better over the last decade or so. So now this is kind of problem that occurred just about a month ago in Neskowin. They're still having landslides and needing to put new riprap up in that area. So our goal over the last couple of years has been to develop a kind of a new approach, a probabilistic methodology to quantify both the present and future coastal flood and coastal change hazards to assess the vulnerability of coastal communities along the Oregon coast. And I'm just going to briefly go through some of the work that myself and several of my students have done over the last couple of years. To do this, we had to come up with a variety of climate change scenarios ourselves, or climate variability scenarios. Here's our range of sea level rise scenarios. So this was work that we started a couple years after the IPCC reports, but before these kind of the National Climate Assessment Report that I mentioned at the beginning of the talk came out. So we had our own, fairly broad range. We had a variety of wave height projections. We let the wave heights continue to go up for a couple of decades, and then we certainly didn't let them go up forever. Waves are not going to become 50-meter tall beasts in 100 years. They can't get big forever. We let them stay more or less the same for the next several decades, and we even had scenarios where the wave heights actually decreased, because again, we know that little about what's actually driving the wave climates. We had scenarios where we increased or decreased the number and frequency of El Niños, and we developed a matrix of a variety of climate change scenarios. I'm not going to go to any of the details of the models that we use in terms of projecting coastal change hazards, but there's a variety of very simple models. In fact, we use the same models that were used by Dogami for the earlier set of maps because we wanted to keep that part consistent. But we developed a series of coastal change hazard zones that were basically a kind of a product of kind of long-term coastal change due to sea level rise, and then the impact of a very major storm occurring at the end of several decades of sea level rise. And here's some of the building blocks of what those models look like. Here's a little stretch of coast in the Neskowin, Oregon littoral cell. So here's just a map of the shoreline. And all I'm showing here is just pointing out that a whole range of scenarios were run. These are projections of coastal change at, I believe, 2100 for this scenario. And we're using a variety of sea level rise scenarios, wave height scenarios, and El Nino scenarios. So that's why there's so many black lines here. And these are just the averages. And the bottom line is we used about 2,000 different combinations of water levels, waves, and morphologies to develop our estimates at each location along the coast. And that's how we were able to develop probabilistic coastal change hazard zones and basically give coastal managers a range of options in terms of what to plan for. So here would be an area that we know for a particular timeline and a particular magnitude event. We're 98% sure that the erosion will get to that point, 50% sure that the erosion will get to that point, and only 2% of our model simulations got back to be this far. And then we kind of put them at a larger scale and again overlay them on communities. We can do that for the present and then at several decades into the future. And obviously, those zones are going to get wider and they're going to move landward through time as sea level does its thing and as the storms get bigger. So these coastal change hazard zones are going to account for a whole variety of things: the storm wave intensity, sea level rise, El Nino occurrences, geomorphology. We've got various time horizons that we're projecting for, various different storm events like the annual event or the 100-year event. And they also have confidence intervals because we're running this in a probabilistic approach. So we think that's a good thing. And one of my master's students, Heather Barron, had a great experience with her project, which she finished last spring. Her deliverable was actually to Tillamook County, and she was able to get her work. She actually turned those zones into nice, pretty maps for the county, and that work was actually adopted into the Tillamook County Framework Plan for Coastal Hazards. And so that was a nice thing for her to be part of a project that actually got her work out to the public right away. And so again, we're incorporating probabilistic coastal change hazard zones into a community planning framework. Now, I won't say that decisions have actually been made yet based upon these maps, but the county has this information as of this past summer. Okay, so I mentioned all the things that they account for. The last couple things I'll talk about, I think I have another couple minutes, is that they also allow us to assess coastal vulnerability and sensitivity along the coast. We can basically assess changes in societal exposure to a variety of hazards. We can look at things like land cover, land use, zoning, the number of structures. So by just using a simple GIS analysis, plot the number of structures within the zones and count them. Think about social disruption during big events when we kind of impact Highway 101, those kinds of things. And so here's some of the results of that work. And again, we can do this for a variety of different events. Here's the annual one-year event, the 100-year event. We've developed these products for 2009, 2030, 2050, and 2100, and again for a variety of kind of confidence levels. We're very confident in the purple, much less confident in the lighter purple out here. But we can do things like for various communities, and this work was done up in Tillamook County, for various communities we can count, again, the number of structures within these hazard zones and basically see that Rockaway certainly has significantly more exposure to these hazards than areas like Netarch, Sand Lake, et cetera. Neskowin also has some issues. And then that was the number of structures within the zone. Netarch had no structures because it's mostly all Cape Lookout State Park, but there are roads, so this is the exposed road length within those communities. Again, Rockaway stands out as a big problem area, as well as Neskowin. We can do things like look at the assessed property value in the hazard zones, and mostly look at actually the dollar amount for each community. Now the state is broken up by community. Here's Rockaway Beach versus, again, Neskowin down here. Again, these communities keep popping out. But we also look at the percentage of the total assessed property of a particular community. And you can see that maybe Rockaway is not quite as bad, but a place like Sand Lake, where it's only a relatively small amount of total dollars that are actually in harm's way, in terms of the percentage of the community, it's a much bigger deal. So the sensitivity of that community to these hazards is a little worse off. And again, here's the assessed property value for the 100-year storm situation. And then just one more thing, you might ask the question in terms of future development. We don't want to have this, this information be, thought of as just a no build. You can't do anything along the coastal communities. Here's an analysis where we looked at the percentage of vacant lots in the 100-year storm erosion zone, and we basically just looked at the percentage of both residential lots as well as commercial lots within these hazard zones. And you can see that it's actually not a huge total percentage of the lots in these communities. So these are the kinds of things we could do with this information. All right, I'll step back now and summarize my talk, but instead of coming up with my own conclusions, what I just did is I took some statements from that IPCC report that I showed you that just came out a couple of weeks ago, because they're incredibly relevant to what I've just talked about. And the panel here on the right, this is a photograph of Rockaway in the northern Oregon coast in Tillamook County, and just kind of point out this very thin strip of sand fronting the first row here of the community. The majority of that community is riprap now because of the problems they've experienced in the past. But the point is that it's very likely, and by very likely IPCC means a 90 to 100% probability, that mean sea level rise will contribute to upward trends in extreme coastal high water levels in the future, and that there is high confidence that locations currently experiencing adverse impacts such as coastal erosion and inundation will continue to do so in the future due to increasing sea levels and all other factors being equal. And so the problems that these folks have had in the past are not going away. If anything, they're just getting worse. I will state that there's very low confidence in terms of our ability to project what the wave climate was, but hopefully one of the take-home messages from this talk is if the wave heights continue to increase, they're going to be as at least important, if not more important, over the couple of decades than just water going up due to the global sea level rise processes. All right, thanks very much. Appreciate your attention. Thanks.
Thanks, Peter. We'll try and take a couple questions, and you almost need this, so I'm going to have to throw this at you, ma'am. While I'm walking over to pass this back, thanks also to Michelle and Theo and Luca for allowing Peter to come down.
Theo's 5 and Luca's 7.
I'm just looking at that photograph that you just showed, and I'm wondering how many places on the Oregon coast is 101 going to be impacted? And I mean, that seems like a huge problem to me.
Yeah, that's a great question, and I don't actually have the slide that has some of the information. We did this analysis just for Tillamook County thus far, and so I can't give you a number for the state, and I can't remember, frankly, what the number was for Tillamook County. But that was one of the things we looked at was the social disruption associated with these major events. If they erode past or cause flooding through 101, it's a problem. I mean, there's certainly many areas that have issues. In this area in south, I think the majority of the issues are associated with landslides rather than coastal flooding and coastal erosion issues. But it certainly can be a problem as well. But it's a great question.
I have a question. Do you ever factor in the magnetic field and the pull of the other planets that might create the high rise of the waves that because of the pull of the moon?
Well, certainly the moon has a very major impact in terms of the tides, in terms of the determinist component. But it's really, in terms of the major changes that we see with the water levels, it's really in terms of warming of the oceans. Okay, so that's the major impact, plus the input of fresh water due to melting of glaciers and ice sheets. Yes, it is. Yeah, that's Rockaway, Highway 101. Yep.
Are sneaker waves on the increase, and how do sneaker waves affect your studies?
Yeah, great question. So those of you that aren't aware of sneaker waves, although you're Oregonian, so everyone should be aware of that. When I first moved here, I thought Phil Knight had something to do with it. Sneaker waves are basically, I talked a lot about wave run-up, so that's the swash oscillations, the water coming up and down the beach. We've got a great phenomena here because our beaches, for the most part, are relatively shallow in slope, and also we have very highly energetic waves. What that does is it forces energy from kind of typical wind waves. We have one wave every 10 seconds. So if you go offshore to these buoys, more or less it's every 10 to 15 seconds. Sneaker waves, meaning there's energy from the wind waves, gets pushed into much lower frequency. So in the order of every minute to 2 minutes, we have a very high oscillation of the water level on the beach face itself. And it really shows up in terms of the swash motions. Okay, and so you can be high and dry on the beach, paying attention to your children or looking back at the parking lot, and then all of a sudden what you thought was a dry beach, the water gets up to your ankles, and that's what a sneaker wave is. The analysis that I breezed over very quickly in terms of what was done at the Coastal Imaging Lab at OSU, we've spent a lot of time focused on the sneaker wave problem and thinking about that transfer of energy to low frequency energy. And all the equations I use for wave run-up, all that information is in there. So we are modeling that low frequency energy. And certainly as the waves get bigger, that component of the swash signal does get bigger as well. In terms of an impact for you in like beach safety, it's not gonna be that big of a deal. We're talking about centimeters or millimeters per year. So, if the water is up to your ankles or, just above your knee, it's not gonna be that big of a difference. But certainly in terms of the analysis, in terms of the total water levels, we are including it. But in terms of the beach safety, I wouldn't worry about that.
Why would one of the slides showed that sea level rise was more pronounced in the higher and the lower latitudes, but not in the equatorial or between, say up to 35 degrees latitude and latitude on either side of the equator. So what would account for that? And the second question is, could you explain a little bit about the IPCC, where it's going, what it's done, and what we should expect to learn from them in the future?
Okay. I'm not an expert in terms of kind of global sea level rise effects. There's a lot of local changes. A lot of the biggest signals that we saw in that plot, that satellite plot for the Pacific, are forced by basically wind stress in the equatorial Pacific. And so we've had an increase in the trade winds over the last several decades, which has caused basically a piling up of water in the Western Pacific. And that's why we see those rates of 10 millimeters or so per year. I can't speak as much to the high latitudes versus low latitudes issues, but that was why we saw that kind of red bullseye in the Western Pacific, and a good reason why we've seen the kind of the low elevations along our coastline. In terms of IPCC, this kind of interim product that just came out in terms of extremes, that's kind of been a major focus. The next report is due kind of 2013, 2014. And in fact, my next door neighbor, Peter Clark, next door meeting one office down, he is a co-author on the sea level rise chapter for that. And so I haven't talked to him recently, but I know that they're working actively on that. So that's about all I can add for the IPCC.
I have a question here on, since a lot of people like to live along the ocean, and I've been down in California too where the mudslides, and when the houses go into the ocean or on a landslide or anything, people are still going right back, and they want to be right on the ocean. I guess up here in the Northwest it's the same way. If they put rocks or retaining walls, they seem to have enough funds to carry out what they want to do, and I can see what you do. It's a little risk doing it, but people still do it. Could you comment on that?
Yeah, Oregon is one of the few states in the country that actually has a policy based upon the beach bill that was passed in 1967. The Coastal Zone Management Act, I think, was 1977. Basically, it's illegal to put rock structures on a coastline now for communities that weren't platted prior to 1977. So there's quite a few places along the Oregon coast where we actually can't put new hard rock structures, and occasionally that gets tested. There's a famous case of the Capes in Tillamook County back in 97, 98, where Senator Hatfield at the time actually had a house. The case went all the way to the governor. That was Kitzhaber's first round as governor, and he actually denied a hard structure at the base of that development, and in fact, several houses were lost. We mentioned at the beginning that I recently went to Sebastian Shores. That's an area, again, a relatively new development. They have an issue more in terms of stream migration. Hunter Creek has migrated to the north every couple of decades, and it's impacted significantly a development there. They're not going to be allowed to put hard rock structures out there to protect their properties. But the state is working with them. They're going to be able to do something in terms of either a beach nourishment or working with kind of natural native materials like tree roots, et cetera, down trees. So Oregon does have one of the few kind of policies in which we actually can't put those rock walls. But you see from this picture of Rockaway, what happens is as the water level continues to come up, when you have an entire community like this armored, you start to lose the beach incrementally because the water gets higher and higher. It spends more time up against the hard structures. And so one of the things we value very much here in Oregon is having public access for recreation on the beach. If the water is up against the hard rock half the time, then we're going to lose that. And so that's one of the negatives associated with the rock structures.
Hello. From time to time, you hear something said about the possibility of a 100-year storm. Could you speak to when that could possibly logically happen and what the results would be to us on the South Coast?
Yeah, it's a great question. So really what we mean by the 100-year storm, it's sort of a misnomer in some ways. And in fact, FEMA's kind of to blame for getting that out in the lexicon. It doesn't mean a storm that's going to happen every 100 years. It means there's only a 1 in 100 chance of it happening this year. Okay? So it could happen tomorrow. It could happen next year. 3 of them can happen next year. But based upon the data set that we have, there's only a 1 in 100 chance that it could happen in any given year. So one of the things that we're trying to do with these hazard maps is to project what the annual big storm will be. So it's a storm about a 10-meter wave height with a relatively high water level, plus the big one. So the 14, 15-meter wave height at a very high water level as well. So that's when we try to do these probabilistic approaches, we're trying to take that into account. We've got a low confidence that it will happen, so there's a low probability that it would happen, but it's at least on the map so people can make decisions accordingly.
Okay, ladies and gentlemen, I'm sure that Peter would be willing to stand in the lobby for a couple minutes afterwards and answer some additional questions. You may have seen the Struva posters for Arctic sea ice. If you have any place that you might be able to post those around the community, I'd appreciate you taking them if there are still some out there. If you didn't have an opportunity to sign in, you could do that. And also, if you're interested in copies of Geology of Pacific Northwest or David Montgomery's signed book, I'll be out there in a little bit as well. But thank you, Peter, for coming down.
Thank you, Ron. Appreciate it. Thank you.
And thanks to all of you for coming out on an incredible night. And hopefully it's still bright and sunny out there. Thank you.